Today we'll begin to discuss electric conduction first through intrinsic type semiconductors. So these intrinsic type semiconductors are extremely pure semiconducting materials. For example, silicon, germanium, these are pure semiconductors. They lie in fourth group of periodic table. Their conductivity can only be controlled with the help of factor temperature. On heating, conductivity of intrinsic conductor can be controlled. So this is its first property. We'll proceed further to study conduction through such intrinsic semiconductors. For example, you consider the solid crystal, suppose of silicon or germanium, lying in fourth group of periodic table. The atomic number of silicon germanium is 14. So, with electronic configuration, in their last valence orbit, they have 4 valence electrons. If you draw sketch the diagram of silicon solid crystal, we get the diagram like this. It has 4 valence electrons each atom. In the crystal, the distribution of atom is periodic and arranged regularly. So if this is one silicon atom, this is second silicon atom, equidistant, this is third silicon atom, upside, downside, everywhere we get their arrangement in crystal regular and periodic. So what happens here? Each silicon atom has 4 valence electrons. One atom shares its 4 valence electrons with neighboring 4 atoms, and it takes 1 electron each from neighboring atom, and every atom completes its octet. Octet means the last valence band they try to fill completely with sharing of electrons with each other. When sharing occurs, we get formation of covalent bonds in between the pair of any 2 silicon atoms. So silicon, it will share its own 4 valence electrons with neighboring 4 atoms, and it will take 1 electron each from its neighboring atom. It will share its, and it will take to share the other electrons with the formation of covalent bonds. This sharing is possible when crystal is formed. So this is electron, this is electron. Each atom gives its one to the other in the pair and receives one from the other, so that each atom has valence band, valence orbit completely filled. So this is silicon structure for pure semiconductor, pure, no impurity is added. So what happens at absolute zero temperature, or even at room at absolute zero temperature, no electron is extra, unbound, which is available for conduction. So at absolute zero temperature, we don't get any conduction through pure semiconductors. But what happens when the temperature of crystal is increased and is made equal to room temperature or maintained at room temperature, each electron receives thermal energy and few covalent bonds break. Few only, not each and every bond. So few covalent bond breaks due to thermal agitation and few electrons set themselves free from valence band. So if you consider energy level diagram, energy band diagram, initially still we are suffering the connectivity problem. Stay tuned. Today we are facing connectivity problem. Why is I don't know bleeding? Today today we are facing today we are facing the connectivity problem. Stay tuned. We will continue the same. So with energy level diagram, this valence band at 0 degree centigrade at absolute zero is completely filled and conduction band is totally empty. No single electron is available for conduction. But at room temperature, due to thermal agitation, few electrons receive energy. They break their own covalent bond and jump into conduction band. So these are thermal electrons. The number of electrons raised to conduction band creates lack of electrons in valence band, and lack of electron is called hole, which is considered as positive charge carriers. So these are thermal electrons and these are thermal holes. So number of electrons and holes are equal. When one covalent bond is broken, it gives rise to one electron hole pair. So number of electrons and number of holes are equal in number. We can write Ne, number of electrons, equal to Nh, number of holes. So this is the specialty of pure semiconductors, which are intrinsic type semiconductors. Both the charge carriers are available for the conduction of electricity. So at this position, if we apply potential difference across this such crystal, then you get two paths of conduction. One path through conduction band for electrons and another path for charge carriers which are positive, that is thermal holes, through valence band. And total current across this pure semiconductor, intrinsic type semiconductor, is thus current due to holes in valence band. Lack of electrons gives you the production of positively charged carrier hole. Equal numbers are there. So it will be then IH plus IE. So in pure semiconductors, intrinsic type semiconductors, current is due to addition of current due to holes and current due to electrons. This is its speciality. Both the carriers are available for electric conductivity. You get electron current through CB and you get hole current through VB, valence band, and hence total current is IH plus IE. Whenever one electron jumps in conduction, one hole is created in valence band and hence Ne is always equal to NH. But what happens even the temperature is raised further beyond the room temperature? 1 minute, I am just checking. Today we have a lot of disturbance for net disturbance for so stay tuned, don't leave. Whenever there is no internet connection, we have to wait, don't leave. So this is intrinsic type. So intrinsic type has three basic features. Current carriers both types, both paths equal in numbers and only can be controlled depending on the temperature of the semiconductor, pure semiconductor. So this is the specialty of intrinsic type semiconductors. Even temperature is raised, number of electrons hole. Voice is not clear. Okay, I will try. Now are you getting? Now are you getting? Today a lot of trouble, net problem. So you might get the problems. Be tuned. So we'll proceed further. So here, this is intrinsic semiconductor, energy band diagram, valence band, valence band. Still you are not getting any voice. Actually everything is as usual. Wait for a while. You will receive the voice. Video is blurred, madam. Setting is perfect. Nothing new. So try to understand the technical problems. We will proceed further. So this intrinsic type semiconductors, in such semiconductors, the electric conductivity is very poor. Even its temperature is increased, you cannot increase the value of IH and IE beyond certain limit, and they are useless for any daily practical purposes because their conductivity is very poor. So that we have to increase the conductivity. So the conductivity of intrinsic type can be increased by two methods, either heating it, and the second method is called doping. But when you operate intrinsic semiconductor with doping process, their properties permanently get changed. After doping, you get one more type of semiconductors which are called extrinsic type. So doping the intrinsic semiconductor, it can be permanently converted into extrinsic side semiconductors, and they have a large electric conductivity. But permanent deformation occurs in intrinsic semiconductors. So that is the same. So with adding impurity, suitable impurity, the conductivity of intrinsic semiconductors can be modified permanently. So we will move further to consider extrinsic type semiconductors. So extrinsic type semiconductors have better conductivity over the intrinsic type, and they are more useful for further practical purposes. So we will switch over to extrinsic type semiconductors now. So here what happens when you prepare extrinsic type, the basic is the pure semiconductor crystal, and this pure semiconductor crystal, sorry, since troubled here. A lot of trouble today for network. Stay tuned. Stay tuned. A lot of trouble. I am trying my level best. I trying my level best. I am trying my level best. See, here we are getting today a lot of network issue. So stay tuned. I will wind up within 5 to 6 minutes. Stay tuned. So extrinsic semiconductor are prepared from intrinsic semiconductors. What is done here? A impurity, suitable impurity is added in this intrinsic. The impurity are the elements either lying in fifth group of periodic table or lying in third group of periodic table. The base is called host and doping impurities are called dopants. When you add fifth group element like phosphorus, antimony, what happens? Silicon, pure silicon. One impurity atom replaces one silicon atom. Suppose antimony. These impurities added are very small in amount. The added impurity should not disturb the crystal structure of the original host, that is the silicon material or germanium material, etc. So the way they added and their measurement is ppm per millimeter. So in very short amount these are added. If you add fifth group element, then what happens? Antimony has 5 valence electrons. What it does? It shares its 4 electrons with neighboring silicon atoms with formation of covalent bonds. It takes one from each silicon atom nearing. It gives its one to each silicon atom to its neighboring. Still, one electron remains unbound and it gets loosely bound with this antimony or fifth group element atom. This electron is free. It donates this electron. This electron is negative charge carrier. So this impurity is called donor impurity. And since large number of donor electrons are available, this extrinsic type semiconductor is called N-type semiconductor. If you add third group element, so that it will not disturb the structure of original silicon, original intrinsic semiconductor, this way only you have to add. So if n type में क्या होता है? If I draw energy level diagram, so what happens now? This fifth electron which is loosely bound, which is of donor type, the impurity donates it. So fifth group elements are called donor impurities. They donate electron. So what happens? This is conduction valence band. This is conduction band. So in valence band, due to thermal agitation, few electrons are already up. So these are thermal electrons. Same number of holes are prepared in valence band, which are called thermal holes. In addition, you get donor electrons. These donor electrons can be raised in conduction band by receiving very small energy. So donor electrons form new energy level which is close to conduction band, and these donor electrons lie over here. So these are donor electrons. So in addition to electron hole thermal pairs, donor electrons are available in large number. and they form intermediate new energy level. By receiving a little energy, they can jump into conduction band and readily available for the conduction, electric conduction. So electric current is due to majority charge carriers which are donor electrons. Due to thermal agitation, you will get these thermal electron hole pairs, no doubt. But in addition, you get large number of donor electrons due to addition of impurity in the original crystal, and hence such is called N-type. These donor electrons form intermediate energy level. They lie in this intermediate energy level, which is called donor energy level. This nu is created and this lies near the conduction band. They can easily jump in conduction band, and this is called N-type extrinsic semiconductor. Instead, if you add third group element as an impurity, what happens? Third group element, indium, is the third group element. It has 3 valence electrons. It shares its 3 electrons with neighboring 3, but it receives fourth electron from fourth silicon atom, but it cannot share extra electron to this silicon atom, and absence of electron creates the positive charge carrier hole. So these holes are created large in number in p-type semiconductors. So to form p-type semiconductors, which are extrinsic type, impurities from third group of periodic table are added. They are added in such a way original crystal structure will not altered, will not get modified. So in p-type, we get positive charge carriers in large number. So absence of electrons creates positive charge carrier. We will call it as hole. So when you draw energy diagram, come. Yeah. Madam has already come. I will ask her to wait for 5 minutes. Don't leave. Computer madam, biology madam, both are waiting for 5 minutes. Let me wind up and then I will close the meeting. So in valence band, along with thermal holes, in conduction band, along with thermal electrons, both should be equal in a number. You get additional holes which are delivered, and that holes are able to accept electrons, and hence what happens? These are called acceptors. So these charge carriers are acceptor. The impurity added is called acceptor impurity, and extra holes created, they form new energy level. These are acceptor holes. This energy level is very close to valence band, and by energy these extra holes can be in valence band. So in p-type, majority charge carriers are holes. The current is due to majority charge carrier holes, and these holes are very much greater in number in comparison with number of electrons available. Here 3 holes will be 3 plus number of acceptor holes. So majority charge carriers are holes, and hence such in extrinsic type conductor is called p-type semiconductor. The charge or the current is majorly due to majority charge carrier holes. So this is about N-type and P-type extrinsic semiconductors along with their band diagram. So today due to disturbance we wasted. Sorry for it. The internet trouble may come anytime. So stay tuned always. Don't blame on anyone. So today we have completed what are extrinsic, what are their types, and next time we'll proceed further for junction. So I am winding up the meeting. So for everyone, thank you.